afternoon, folks. So I'm going to be talking about Unikernels. Essentially, I'm going to give a brief overview as to what they are, how we got here, and where they're going to be useful in the future. And one of the first things I do when I give a talk is just thank everyone who's ever contributed to open source software, because everything I'm going to talk about and show you has been contributed to by hundreds and hundreds of people all around the world. So the fact that I can stand up here and talk about it is because of all the code that other people have pushed. So briefly about me, my name's Amir. I work at Docker in Cambridge in England. The main area that I work on is Unikernels, although obviously we work on a lot of other things to do with Docker as well. So if you want to get hold of me at any point, my Twitter handle is up there. You can post questions there, and I'll try and get to them after the talk. So to start off with, let's think about what software is like today. And so typically, it's an application which is made up of the language runtime, your application itself, and some configuration. And we typically sit that on top of something called an operating system. And that application tends to make a lot of assumptions about the operating system that it's sitting on top of. And I'm talking about traditional OSs here. But before we go any further, we should think about what this actually means. So what is this thing that we call an operating system? And why do we have this separation of these two things where we have a thing that we put on top of another thing? So to think about that, we'll have to actually go back in time and have a very short history lesson. So let's go back and think about the history of how we ended up with OSs. This is the Electronic Delay Storage Automatic Calculator, also known as the EDSAC. So this was based in Cambridge University, and this went into service in 1949. This was a production system in that it had users. The reason it existed was to solve problems for other people in other research groups in other departments. So the customers for this, the actual real-life customers, were researchers from areas like chemistry, medicine, and physics, because it had numerical processing that they needed to get done. And in fact, there were Nobel Prizes awarded as a result of the work that was done on this EDSAC. So that was for chemistry, physics, and medicine. So this was a computer where people submitted their code to. It did work, it crunched those numbers, and it provided output back to those users. So it was a production system in that sense. But how did you as a user program for this environment? Punch tape is what people used. So these were literally, as you see, punch tape. And this was how you programmed the EDSAC. And your punch strip, if you're a researcher, you had to come with your punch strip, and that had to contain everything that your application needed in order to run, all right the way through the stack. So this was really full stack programming way back then. And that meant needing to understand how the computer systems work, all the way up to the bit that you actually cared about, which is your application, the thing that you wanted to do the number crunching on. So your code had to be completely self-contained, one strip, and that would be what would fit in. And if it completed, you got the result returned to you. If it failed, you got the error sent back with the memory location where something went wrong. And then it was up to you to go and figure out what was wrong with your punch strip and fix it. So code reuse seems a bit difficult. So it's obvious that many people can have the same things that they want to do repeatedly. So another invention happened around about the same time, which is that of the subroutine. Now this is taken for granted, but this is actually a really important advance, because this is what allowed code to be managed and reused both across and within programs. And in fact, subroutines were kept as a master tape, and users could then copy those routines to the end of their program. And that was actually where the concept of a library came along, because subroutine libraries were put together, and they were indexed, and you actually go and look for specific functions that would help you with your programming needs, and then add those to the end of your code. So the users at that point could then focus on what their application needed to do, and just pull in the necessary libraries that they needed to solve certain repeatable problems. And so we ended up with a large collection of these subroutines. I think there were about 84 around the last time I remember. And so all of these were reusable. So some of these became useful to have loaded up at the very beginning. So runtime libraries that were called at the time. And this is essentially the birth of the operating system, the thing that runs first that allows your other applications to run much, much easier. So what does an operating system do? It does a whole bunch of things. So the bubble that is interesting here is that thing on the top left, which is, oh my God, this operating system sure is helpful. And it is, because the OS took care of a lot of things that you, the user, didn't need to worry about. It made it much easier for you to come along with your application, make a bunch of general assumptions, and then your application would run the right way. And the OS would take care of a lot of the underlying details for you. But the OS in this example is quite large and monolithic. This example here, it has to serve multiple users, has multiple processes, And there's a tendency for the user to assume that everything it might need is there. And if it's not there, then there's an argument for upstreaming new code into the operating system so that users can benefit. But we should remember the kind of model that this approach worked for was when we had machines like this. We had big machines where we had lots of users all trying to use the system all at the same time. So the basic premise is hardware that's shared amongst users. And this model existed for quite a long time. You would provision hardware, run some kind of operating system on it, and then you give users access to that. And that was all great so far. But of course, things changed. So if we fast forward a long time, this is more of the model that we have now. So this is the cloud. This is essentially other people's computers. So now you're taking your code and shipping it somewhere else. So when we ended up here, it was more about the ability to provision and manage virtual machines. So the users were still in control, and they had more control. But the thing that happened at this point was we carried a bunch of assumptions forward into this new era. Assumptions that were originally appropriate for the time when we had big operating systems on hardware, but now in a world that has much more virtualization. So carrying forward those assumptions leads to a bunch of issues, and we'll come back to those a little bit later. And right now, we're still living with the legacy of these full-blown operating systems. So let's go back to where we were before. So software is an application that runs on top of an operating system. The operating system essentially has to cope with multiple users, multiple things, all trying to compete for attention. Another way of looking at the same thing is that's your application sitting on top. That's the bit that you care about when you deploy your code. But it doesn't need everything that's in the system. It needs some of those libraries that are available. It needs some aspects of the kernel, but not everything. And there's even things not shown on this diagram, for example, a shell, utilities, services, that you may not care about when you're deploying your code. Yet another way of thinking about this is at the top there is the code you actually care about. That's your business logic, let's say. That's the bit that makes you the money. That's the bit you're actually on the hook for maintaining. Everything else underneath is code that the operating system insists that you need. It's just there all the time. And in case you're wondering how much code there is, I was at LinuxCon recently, and it was mentioned that Linux now has something like 21 million lines of code. Does your next project really need 21 million lines of code? So a slightly less charitable way of looking at this is something more like this. So there's your good ship on top. That's the code. That's the stuff you actually care about. And underneath is this huge, humongous beast. And you don't really know what's down there. You're not quite sure what it's doing. You hope it's benevolent. But it's there all the time. So to carry on this, we have this model of building software that runs on an operating system, and we build this software locally. But as I mentioned already, we deploy it remotely, so there's already a disparity between how we build software and where we ship it to. And this is going to get even more complicated when we think about things like the Internet of Things. So we're going to be deploying our code even more remotely than we were before. And if you don't believe that you in this room are going to be deploying Internet of Things devices, just bear in mind that decades ago, people thought they were deploying code that would never be connected to the internet. So, in case you're thinking that Internet of Things devices are just toasters that tweet and fridges that order milk, just look at the bottom left of that slide. That's an insulin pump that talks to a phone application. Right next to it, just to the left of that, is a wireless internet-connected pacemaker. So there is software running on this device that is connected to the internet. And if that doesn't give you pause for thought in terms of how we write software, I'm not sure what else will. And things do go wrong with these products today in terms of the software that they run. So this was a tweet a few months ago from a security researcher called Marie, who has one of those pacemakers installed. Essentially, there was a problem, and the pacemaker required programming, and she was in the air while this happened. There are literally lives at stake in terms of how we deploy software now. And if pacemakers, I mean, I'm not sure if anyone in the room has one, but if this doesn't convince you, well, here's another example of why software matters. So the Dyn outage that happened a few months ago essentially managed to take down large portions of the internet. Now, bear in mind that the internet was originally designed to withstand a nuclear attack, and it's been taken down by webcams. And this is all because software today is complex. There are a lot of moving parts. It's grown over time. It's grown organically over time. Even though most of the applications that we now ship tend to do only the one thing, especially for deploying things to the cloud. Of course, things are getting slightly easier. So Docker has helped shift Docker and containers have helped shift what the unit of deployment is. And that's provided some more consistency between developers and productions, especially where we have different environments across the two. And Docker also provides a containers as a service platform, which kind of sits in between infrastructure as a service, which can be quite low level, and platform as a service, which can sometimes be too opinionated. So containers as a service is aiming to hit the sweet spot. But of course, technology like this still allows you to bring legacy ideas forward. So when you're carrying the legacy assumptions forward, you're bringing all the assumptions that were embedded in that code along with you. So one classic example of this in the era of Docker is things like this. If you're building your image and you're basing it on an existing distro, that's great, you can work. But you're then pulling in all the assumptions that were baked into that. It's not always necessary, but of course we do this because it's easy. So what if we took an extreme view? What if we took a step back and looked at the world as it is today in terms of how people write and ship software? And what if we said we can start from scratch? What would we do differently? And this is, of course, what led to the idea of unikernels. So unikernels are constructed from library operating systems. And so this takes us back to the idea of all those reusable libraries that we had that I mentioned back when I was talking about the EDSAC. So the idea is you construct a unikernel from a library operating system. The operating system, you then break up and make it available as modular components. You then link only the system functionality that your application will actually need, and then you compile that down into a unikernel. And now that you have a bunch of reusable libraries, you can target alternative platforms just by swapping out the system libraries underneath. And there are many, many different unikernel implementations out there today. So and people are referring to this as a zoo of unikernels. This is just a selection of them. There are more than this already. And I was talking with someone yesterday evening about yet another node-based one. And all of these are in various stages of development. Some of them are more mature than others. But there are two broad approaches. One of those is to consider legacy, and the other one is to go completely clean slate, starting from scratch. So what does consider legacy mean? So that's essentially taking software from existing stacks. So for example, Rump Kernels, the project, takes NetBSD, breaks up into reusable components so that you can for example, take the networking stack and use it in user space. And LKL, which is the Linux kernel library project, is aiming to do the same with the Linux kernel. So these are essentially maintaining POSIX compliance, allowing you to take legacy software and try and run them as a unikernel. The others take a clean slate approach. And the ones that go clean slate tend to be much more language specific. They have to rewrite the libraries that are in the system. For example, many of these projects have had to rewrite the networking stack. But on the plus side, you can do away with POSIX and instead have clean APIs to interface with everything. And you can also benefit from the OS-specific package management that is out there. So I'll talk about one of these in a little bit more detail, which is MirageOS. That's the one I'm most familiar with, and that one is written in a language called OCaml. How many people have ever heard of OCaml in this room? Ooh, a few of you. That's nice. So what MirageOS tries to do is essentially take this stack, make those components available as libraries, and then allow you to compile that down into a unikernel. So a lot of work has already been done to create create the system libraries that you will need. And because those system libraries exist, you can target multiple different backends without changing your application code. You just need the system libraries to exist. So I'll be hopefully showing you a little bit later how we can deploy to Zen on x86 and on ARM, and other people have contributed different software stacks for different backends. So the important thing to remember if you're using the clean slate approach, and in this case of Mirage, is you have a very familiar development cycle. So if you're used to using certain tools, those tools are still available to you, whether that be if you're using OCaml, if you're using Haskell, or any of the other clean slate implementations. But the deployment scenarios are quite broad, because you can now take that same code and then retarget it to different environments. So just to underline that point, all your usual tools are available to you. All your normal debug tools, all your normal ways of creating your application. So as an example of this, I'll talk through a static website that we built and compare that with what it would have been like had we built it using a traditional stack. And what I'm going to describe is actually applicable to any application. It's just that static websites are fairly easy to reason about because I'm sure most of you understand what is involved in building one. So the one I'd like to talk about is the Bitcoin Pinata. Has anyone heard of this one? Show of hands. One. So the Bitcoin Pinata is essentially a static website that holds the key to a private Bitcoin address. In other words, it's holding about 10 Bitcoin. And it doesn't do anything except sit on the internet and trying to make TLS connections. So the aim is, if you can break into this and extract that key, you then get to keep the Bitcoin. So it's somewhat like a bug bounty program, except you don't have to tell us that you broke it, you just take the coin. So it was novel in that respect, that if you manage to break in, you just get to keep what you find. So this was built as a Uni kernel, and there is nothing in this stack that it doesn't need to be there. So we rewrote TLS using a camel. There was a functional core, and there's way less code, especially if you compare to things like OpenSSL. This service has been running for about a year and a half now, maybe coming up to 2 years soon. It's had tens of thousands of attempts of people trying to hack it, and it's still sitting there. And it's an extremely lean service. Now, of course, the fact that no one's taken the coins is not proof of security, but it does indicate that the stack is stable, as in it's been up that long, it's been on the live internet, it's had attacks, and it's still running. So, if we say this thing on the right that's the website running in there, and that's a traditional stack, how much smaller do you think the Uni kernel version of this is? Anyone want to shout out some guesses? 1,000 times? Go with that, okay. I wish it was 1,000 times. It's 4% the size. So that thing on the left is 4% the size of the thing on the right. The thing on the left does the same job as the thing on the right, except it is 8.2 megabytes in size, and that contains everything, right the way down from the application code, that static website, right the way down to the networking stack and everything, 8.2 megabytes. About 102,000 lines of code, all written in type-safe. Nearly all of it is type-safe, a camel, and that's robust and it runs on the internet. Whereas its equivalent on the other side would have been about 200 megabytes with way more, 25 times more code. And of course, it's doing the same thing, the thing on the right. The same thing, but somewhere in that stack is our old friend, because there's a bunch of things going on there, a bunch of processes that we don't really understand. We don't really know what that system is doing. And at this point, it's useful to remind ourselves, what about the relationship between something like unikernels and something like Docker and containers? So the thing to remember here is that these aren't competing technologies, these aren't different things. They essentially sit on the same continuum. And that continuum, if you think about it, is on the one hand, you have a traditional operating system. Then you can think about increasing isolation and specialization. You can have containers that share a kernel. You can then think about reducing the size of that kernel. So this is where things like Alpine Linux come into play. And if you take that progression to its natural extreme, that's where you end up with something like unikernels, which contains only the stuff that you put in it and nothing else. So that's the idea of this continuum, of this spectrum of the traditional way of doing things, a containerization way, lean, very, very small distributions, and then right the way through to what a unikernel is. And a unikernel is essentially building a bespoke OS just for your application and compiling everything in together. So a brief recap now of what unikernels actually are. So they're highly specialized. So you build specialized services with these things. It is not a general purpose computer. It is not a panacea. It's not going to replace the way we do all our computing, but it will be useful for certain parts of it. They sit on continuum containers, and you can have robust deployments because, as I mentioned, we've had services that were long-running services that have sat on the internet and actually been perfectly stable. And the other benefit is that everything is a library. So all the components that go into building the unikernels are reusable components because they're just libraries, just the way that all the existing libraries that exist in package management systems are. And there are quite a few benefits to having libraries like that, the reusable libraries. So in terms of deployments of unikernels, there are a number of them out there now. So people have built, there's the Bitcoin Pinata I mentioned, people have built REST services, people are building to-do apps, lots of different things are out there. There also are now production uses of unikernels as well. So Cyberchaff is a product from a company called from a research agency called Galois, and they essentially use HalVM unikernels and distribute them on a network. So what Cyberchaff does is essentially distributes, it looks like a vulnerable version of Nginx or a vulnerable version of Apache sitting on your network, except it's not. It's a unikernel that's pretending to be that. And the idea is this will detect the second step in a network intrusion. So if someone attacks your network, the first thing they want to do is try and attack the next machine in the system. So if you have thousands of these essentially fake devices sitting on your network, this may be one of the ones that they attack. And so if anyone makes a connection to one of these unikernels, then a network administrator can be alerted, and then they can decide what to do next, whether to let the attack play out or sequester them off or shut it down. And this is possible because unikernels are just so small and so easy to maintain. You just deploy them and then ignore them. Trying to do something like this with a traditional stack would have been much more complicated. And so that's one approach. Another one was a network function virtualization platform that was built by folks at Ericsson. So what they did was take the unikernel approach and essentially architect the system in such a way so they have one unikernel that has a networking stack and all the other unikernels can communicate by other means. And then they access the outside world through that one unikernel. So they can build platforms using these technologies. But of course, libraries mean you can reuse libraries, and you can use them to solve other problems elsewhere. So has anyone ever used Docker for Mac? Okay, you have used Mirage libraries, Mirage OS libraries. So we've taken the networking stack of Mirage OS, and it's sitting there in Docker for Mac because it's helping to deal with issues of how people behind a VPN get their containers to access the internet. And that was because we had a library sitting around that could solve a problem in a different domain. So this is one of the important benefits of having libraries. So now let's move on to when you should use unikernels. So as I mentioned before, this is not a case, they're not going to solve every problem out there. They're going to be certain use cases. So the question is, it's about the right tool for the job. So each of these is, so to draw an analogy, each of these is a vehicle from getting from A to B. But you use different ones in different contexts. For example, you probably wouldn't go to the shops to do your shopping using an F1 vehicle. You might. So it's a case of finding out where unikernels fit in this ecosystem. So let's go back and think about what the properties are of unikernels, some of the things I've already mentioned. When you build them, you build a single service, one thing. It's not doing multiple tasks. You essentially will end up with a distributed system, multiple different unikernels doing different tasks. You can deploy each of those independently of each other. You can have diverse tech choices in there, so you can have different unikernels running alongside different other technologies, depending on your architecture. So this just naturally lends itself to the idea of microservices. Quick show of hands, who in the room is using microservices, like that architecture pattern? Who is thinking about moving to that architecture pattern? Okay. So the pathway to unikernels today, if we were to think about it, is very similar to the pathway towards microservices. So to get towards a microservice, if you have, most software is probably going to be something like this. You have a monolith, one big thing that you deploy that does a bunch of things. So the first thing you want to do there is try and break that up. Essentially trying to figure out where the dividing lines are between that monolith and what separate components are in there. And then you need to start breaking off some of those components into separate microservices. And if you carry on this progression through, you can end up with a collection of different microservices all working together. And this is a place where tools like Docker can actually help. So the pathway will look something like this. So essentially you go from your monolith to a broken up system to a much more distributed system. And some components in that system might make sense to rewrite as a unikernel. Now, I'm not suggesting any of these steps are easy. Even that first one, deciding where the boundary lines are, is probably more complex than you realize because they may not be quite where you think they are. The second step is also going to be more complicated because now you have a distributed system which creates a bunch of other issues in terms of operations that you have to then handle. But of course, there are benefits to when you end up to the system on the right in terms of the ability for your teams to deploy things quickly. So that's essentially what the pathway right now to unikernels looks like. But what about whether they're production ready? Now, it depends on what we mean by production ready, because it means different things to different people. So I'm going to draw another analogy now, going back to the vehicles I mentioned earlier. So this is a Daimler 1899. This was out about 9 years before the Ford Model T. So the Ford Model T is a car that went to the mass production. People had cars back then. And when they had one of these cars, they were probably reasonably well off, and they probably had an understanding and the ability to fix it if it didn't work, to get their hands dirty, to roll up their sleeves and change parts, change the oil, or they'd have someone on staff who could do that. If we fast forward just over 100 years or so, cars are now more like this. This is a Tesla. This is probably mostly driven by software. If there's ever an issue with this car, it will probably drive itself away to a garage to fix itself and then come back. This is the opposite of the car I just showed you before. But this is a useful analogy, because if you want to think about whether or not unikernels are production ready, it depends on you. Are you someone who's going to get hands-on? Do you consider yourself to be more of a mechanic? So if something doesn't quite work, are you going to write a library to help fix it? Are you interested and curious enough to get hands deep into the code and fix things? If so, then yes, unikernels are production ready for you. If you're expecting something that is much more convenient, much works out of the box, lots of the problems have been solved, how we then manage these at scale has been solved, then it's not quite ready for you, because we have to do much more in terms of tooling, much more in terms of monitoring and logging, all those extra things that we expect to have in order for you to have essentially a works out of the box experience. So at this point, I'm going to show you a brief demo of building a Mirage OS unikernel. Do you want to see that? Okay. So the demo I'm going to show you is building something on a Mac, which is this machine. I'll be using Docker for Mac to do that. And then I'm going to deploy it to an IoT device. So essentially, I'm going to build and run an app in a Linux container. I will retarget that app for the ARM backend without touching the code. And then I'm going to deploy that artifact onto an ARM device. And my proxy for an ARM device is this little thing here. So this is a cubby board, and this is my IoT device. So the demo I'm going to show you is the 2048 game. You guys know what this is? Okay, so this is essentially running as a static website. And because I'm going to have a bunch of terminal windows open, I put this together just to give you a brief guide as to where I am in the demo so you can keep up. But if at any point you're not sure what's going on, please shout out. So at this point, I will now drop out into my demo, and I will cross my fingers that hope that everything works. And I can't see what's on the screen, so I'll be craning my neck a lot. Okay. Okay, so here we have a bunch of files. I should have cleaned this up before. So only a few of those files are actually relevant. So this is the game, and this is the file that actually defines that application. So this is a Mirage OS application, Mirage OS unikernel, and config.ml is where everything is defined. And so what I'm going to do now is launch a container with, I'm going to launch a Linux container. I'm going to type this out by hand, but if it doesn't work, I'll copy paste it. I'm going to mount the volume. If you notice a typo, do shout out. That's wrong. That should be this. And I'm also going to sort the ports out. 80, 80, 80. Okay, so this is a container that I built earlier for the purposes of this demo. Work. Yes. Okay. That didn't work about 10 minutes before the talk. And I have some housekeeping to do in here. So now I've mounted that, so you can see all the files are already here. Let's actually clean up before we carry on, because not all those files are necessary. Okay, so this is actually what, if you were to clone this repo, this is what you'd actually get. So now what I'm going to do is use Mirage. So the Mirage tool is already installed on here. Oh, and just to show you exactly where we are. So this is a Linux container. So now we're going to do Mirage configure. I'm going to tell it that the target is the Unix backend, because Mirage allows you to target multiple different backends. Unix is one of those backends, so it will run as a Unix process. I can also tell it to use what to do in terms of networking. So this can all be configured in the config file, or you can pass them as command arguments. And OPAM is the package manager for a camel. And I'm telling it not to use the package manager, because what the Mirage tool would do is go off and fetch any packages that you need but you don't have currently installed. Because I built this image, I know all the libraries I have are already in here, so I'm going to tell it not to do that, and that will save a few seconds. So now what has that done? So it's generated a few more files. It's generated a make file. Okay, So it's generated a make file. And this is what we're going to use to then build our unikernel. Okay? So now what we do is make. And so there we are. That has built the Unix backend of a Mirage unikernel. And we can actually run that. And that is now running. So we can now switch to a browser and look at localhost. And this should now be there, if I can find my mouse. There we go. So this is running from within the container. And so far, this is all fairly normal. So now what we're going to do is we're going to turn this off. We'll go back to our code. We'll shut this down. We'll clean up after ourselves, because I'm going to mount this again. Okay, so all those files are gone. We're back to where we were before. And now we're going to mount the same directory in an ARM container instead. So just to speed it up. Okay, so what I'm doing here is I am mounting the current directory. I don't need to mess with ports, because I'm just using this to do the build of the binary that I'm going to deploy to this device. Okay, I need to do that housekeeping again. And here we are with the files. And so now we're going to do a similar step to before, except now we're going to, oh, before we do this, I'll just show you that we're in an ARM container. So, yep, this is the ARM container. And now I'm going to tell Mirage to configure for the Zen backend. So what we've done here is the target is now Zen, so -tzen. We're going to get the IP address from this machine. So I'm using the DHCP, and then some housekeeping that I have there with how it's going to work with networking. And again, I'm telling it not to use the package manager, because I know the packages I need are already installed on this in this container. Okay? And it's done as it did before. There is now a make file. Oh, well, never mind. It's there. And we'll just run make, and this will take a little bit longer because we're now in an ARM container. So what the package manager would have done this time is gone off to fetch the other kinds of packages it would have needed to target the ARM backend instead of the Unix backend, and that would have been taken care of automatically. Nothing in my code base had to change in order to do that, and now it's done the build. So we can see what we have. That's all looking good. So now we'll go back to the OSX environments, just logging out of that container. And what I'm going to do now, so you should see everything should be here. There it is. It's the one in red, mir //zen. So that's the binary that's going to run on this device. So let's copy that over So I'm just copying that over to this board. That should have copied. Now let's log into that board. Okay. Here we are. So there we are. That's the file we've just copied in. And now I'm going to run it. So this, now, because this is running Zen, it's going to be sudo excel create. Drop me in a console. Right. So now Zen is starting that, and now it's got an IP address. So now we should be able to grab this address, and we'll look at, so this should have gone. I can't see my mouse. Well, this should have gone. And I happen to know that it's now going to be port 8080. Do that. There we go. So this is now that same code running from this device here, and that game works. So that's an example of taking the same code and retargeting it without you, the developer, having to worry about changing any of your code base. And so you can imagine something like a CI system taking care of all this stuff for you, for all the various backends that are out there and all the new ones that may come along. Let's go back to here. So just a summary of what we did. So we built an application in a Linux container. We then retargeted that same application to run on the ARM backend. So that was Linux container on x86, then it was ARM, random on ARM container, and then we deployed that onto an ARM device. So that's an example of what it might look like to build and deploy such applications. So of course there's a lot more work to do in terms of deploying such things at scale, orchestrating them and all those things. But this gives you a taste of what it's like. And people who are getting their hands dirty are already deploying these things. So it's still fairly early days at the moment. So there's a website called unikernel.org where there's a bunch more information. The range of different projects are listed, and there are posts there that describe some of the use cases that people are coming up with. And I'm very interested to hear from you guys what kind of questions you have, what kind of thoughts you have. So at this point, I'll hand over to you guys.
Yeah. First of all, thank you. Yeah, we have 3 questions in Slido. I forgot to remind you in the beginning, but yeah, we use Slido. So the first question is about production ready. You mentioned possibly having to write libraries. Which libraries are the ones usually missing and lacking functionality in your experience?
So at the moment we have, so all the system type level libraries we've actually written a lot of. So there's a networking stack, there's a whole bunch of stuff that's out there. What's missing is more testing of those libraries. So more people trying to use them and finding edge cases and reporting. Occasionally they'll find bugs, occasionally there'll be performance issues. So those libraries exist, they need to be used a bit more. So for example, we learned a lot when we deployed the Bitcoin Pinata about the networking stack. We also learned more about when we deployed it in a production app that's now with hundreds of thousands of users. So, and also any pure OCaml library, in the case of Mirage OS, is also usable in a Uni Kernel because it's pure OCaml. So the package ecosystem also provides a bunch of libraries.
Okay. Yeah. Next question. If I want to create a Uni kernel for my service written in language with runtime like Ruby or Java, will I end up with a really fat Uni kernel with half of those libraries in there, or is it going to be small?
That depends on the approach that you take. So for something like Java, there are projects out there like rump kernel I mentioned earlier, which you'll be able to take the NetBSD components and then compile your project then as a Uni kernel. It will be slightly bigger. So Mirage OS can produce really, really small output. So for example, we can get a DNS server to 200 kilobytes that is just as performant as a current stack with Bind 9. That won't necessarily be the case if you're taking an existing Java app and trying to run it as a Uni kernel. But you can get quite far. You can get a whole bunch of the benefits in terms of removing code that you're not using.
Okay. Yeah. One last question I have in Slido is Alpine Linux considered to be a Uni kernel too? Because it's quite small.
It's quite small, but this is where it sits in terms of the continuum that I mentioned earlier. So Alpine Linux actually highlights the fact that we're moving from an era where we had big fat OSs to much, much smaller lean ones. And Uni kernels represent that progression, but on a much further extreme. So Alpine is not a Uni kernel, it's still a distribution.
Okay.
but it shows the direction that things are going in.
Yeah, minification.
Yeah.
Any questions from the audience? Oh, I have how to debug. Considering network.
So one of the challenges of deploying a system like this is logging, monitoring, and understanding what's going on with the system. But this isn't specific to Unikernels. It's specific to any kind of microservices pattern that you try and deploy. So if you're deploying microservices where you really have stripped out everything, you then have to think about how do I do logging? How do I then understand what's going on in the system? So in terms of Unikernels, it's possible to deploy something and then if something goes wrong, turn it off, roll back to an earlier version, put something in a sandbox and try and figure out what's going on. Bear in mind, with something like MirageOS, you always also have the Unix target. So you can build in an environment where you have access to different tools. But of course, tooling is a general problem with new things.
Any other questions?
Oh, just to add to that point, so depending on the Unikernel implementation you use, you can use all the existing tools. So rump kernels, for example, you can just attach something like GDB and understand what's going on. But because all the projects are different, they all have different approaches and different tooling.
Any other questions?
For instance, if I wanted to take completely just Unikernel approach to my application, and my application would rely on some external binary that it would execute, should I make it that it doesn't execute this binary anymore and just uses some kind of library, or it would be still applicable, like using Unikernel and also executing some local binaries like ls or...
So in that sense, it depends partly on what the application is. So one of the things that's useful about Unikernels that I maybe didn't mention is immutable infrastructure. So the idea that you build something, deploy it, and then it's not changeable. So if you're pulling in other binaries from elsewhere, one of the questions is, like, what does that binary then assume and depend on? So maybe in that case, a Unikernel may not be appropriate way of it may not be appropriate for that kind of.
The question is mostly just theoretical and technical. So, for instance, if I just wanted to list my root directory, would it be okay to execute ls? Or should I...
So in that sense, the Unikernel won't have a file system unless you've included a file system. So you may not need a file system for a certain kind of application you're deploying. So you would not be able to do what you described. But if you need something like a file system, if you need something like root level access, then maybe this isn't the right approach for that particular application. So the idea is this is not an artifact that you would then log into and then do things with once you're in there. It's an input of a process, and then that artifact is the thing that gets deployed. And if you need to change something, you go back to the source code. Does that make sense?
Yeah.
Yeah, there some questions. Yeah.
So if I have an existing application and I want to run in Unikernel, how do I figure out like what I need in Unikernel? Like what's the process?
That can involve a bit of headache if you're taking an existing application. It's much easier if you're doing something from scratch and if you're using one of the clean slate ones, because then you're building it up. So if you're building a new microservice from scratch, then it's much, much easier to figure out what you need because you just depend on the necessary libraries. If you're taking an existing application, you then have to first figure out what OS assumptions are there in that application and in the libraries that that application uses. And that's where the challenge sometimes lies. So one approach to trying to get around that is to use one of the Unikernel projects that copes with legacy. So you'll then end up with a slightly fatter Unikernel, but you still have the headache of trying to make sure that any system calls are being captured. Did that make sense? Okay.
Yeah, there was one question from the back.
I would like to ask, is it possible to use MirageOS, for example, on ARM architecture bare method without any virtualization?
Is it possible? Yes. Have we done it? I don't think so. Because one of the issues when you're targeting like embedded systems are device drivers. So the device drivers have to come from somewhere. So once we have a mechanism for dealing with that, then yes, we can do that. But for the moment, we get away with it because as I demonstrate on this machine, this is actually running Zen. So there's a DOM0 in there which has a bunch of drivers in it, so we don't have to think about it too much. But the short answer is yes, it's possible. I'm not personally aware of anyone who's done that yet.
Everything is possible. Okay.
compare the Unikernels with serverless architectures, which like Amazon Lambda, which is often referenced as Unikernel example. So serverless architecture has the latency on the startup time, right, which is important and needs to be considered when you write your microservice. So what's the average latency for a start of the Unikernel? And the second question, what are other important considerations that you must take when you write code for Unikernels?
Okay, so just to summarize the question is, well, what's the startup time for a Unikernel? What's the boot times?
Yes, the boot time.
And what are the important considerations when you're building a Unikernel? Okay, so the first question is that they can be booted in milliseconds, so they can be booted very quickly. And there's a paper you can look at on the unikernel.org website called Jitsu, which provides an example of how quickly they can boot. There are graphs in there as well. So they can be booted extremely quickly. And the things you need to be aware of when you're writing code for a Unikernel is, the very first thing is you must strip out all assumptions you have about the OS that you're writing on. So it's very, very easy in the paradigm that we have today to just assume Unix. Somewhere down underneath us in the depths is Unix, and so there's some syscall that goes to Unix clock or something like that. That's an important consideration. So all those things need to be stripped out. The other consideration, depending on how dirty you want to get your hands, is are the necessary libraries out there yet? So we do have a lot of libraries, but there may be certain cases where you need a certain library, it doesn't exist. Is that a library that you want to write and then hopefully maintain? Because that would be wonderful. We need more people to do that. So that's another consideration. And then the final consideration is deployment. Right now is a thing that needs to be worked on. So we can deploy Unikernels, I showed we were able to deploy it, but sometimes it can be a bit manual. So people string together their own little systems for how to build these things and then deploy them. We need to have much more consistent methods of doing that, but if you're doing it now, that's something to think about. So in brief, consideration of for building any kind of Unikernel, make sure you're removing all the OS assumptions, check that the libraries that you need actually exist, and if not, are you willing to write them? And third, be aware that deployment is going to be something that you have to think about.
Okay, there was one last question.
I have like half a question, half a comment. I mean, today also you talk, I sense like a sense of familiarity, because I mean, the idea itself is not new. We can take, for instance, self-executed Java, so-called, we just took the whole Java machine, put it in executable archive along with your code, and you can run it as any other file, but it's inside it's really a Java machine. The second good example is Delphi. It's quite old language, which actually also has an advantage to be built almost without any third-party libraries and dependency, but hello world will cost you hundreds of kilobytes because of that. So I mean, maintainability of Unikernels. Okay, you have something really small, really fast, some buzzbox, right, which just works somehow, but how are you going to deal if you have dozens of such buzzboxes in your corporate network and they do some complex business logic and you don't really have any ways to understand what's inside this box? The only thing you can do is just restart it. So, I mean, how do you see the future of Unikernels in big enterprise projects which has to have some SLAs, which has to maintain some stability over time and provide some means to monitor, to control execution environment, I would put it this way.
Okay, so the first comment you made, I'm going to try and unpack all the things you said. So the first comment was these ideas aren't new. That's correct, they're not new. So these ideas have been around for a long time. We're just revisiting them now that the world looks like a different place. It makes sense to go back and revisit all those assumptions, and this approach now makes much more sense. The other comment you made was, how do we
How do we maintain execution architecture, if you like? So how do we, when application is running and you don't have any means to take the logs, you don't have any means to debug something, you don't have any means to...
So so I would disagree where you say we don't have any means to take the logs. That's something that will just get fixed. So this is not new. This work isn't over yet. There's lots more work happening here. So how we get logs out of these, how we do that in a consistent way, where do you push them to, what happens to those things? These aren't new problems. Unikernels did not introduce these problems. These have existed in any kind of approach, just taking taking the microservices pattern. So those things will just get fixed over time. That's just a matter of appropriate tooling, appropriate approaches, so that will happen. So the other thing you mentioned was how do we keep a check on what's actually running? So if there's a thing and all you can do is turn it off and on again, how do you know what's in it? Is that?
Yes, something like that.
Okay. So that also comes down to the fact that the code that you're deploying is the actual important part. So the version code. So being able to keep some link between the code that gets deployed and the artifact that it's linked to, that's also something that can be solved, essentially, because that's all that matters. You have a box that can turn it off and on again, but what really matters is the code that constructed it. So being able to go back to that code, and for example, we should be able to do reproducible builds, have a manifest of all the things that went into that Uni kernel, including where the code came from, including the libraries that were used. So you can then have provenance tracking all the way throughout the chain. That's something that's achievable, and that's actually going to be easier to do with a Uni kernel approach than it will with a traditional OS approach. Did that answer your question?
Okay, thank you very much, Amir. We're running out of time.